is there any question that I should answer before moving on?
Yeah. So there's a question concerning the quantum verifiers. So resetting does not work only because the quantum psi information is unclonable state. And the question is, that mean in the classical setting, rewinding or resetting would work the same?
Yeah. Classically, they're both the same. So because you can just store, every snapshot of the computation, and then reset means going to the very first one, or the second, and rewinding just going to something in the middle. And quantumly, the problem is that you have the non-cloning theorem that doesn't allow you to copy this side information in general, so you cannot. You cannot just reset it and give the same quantum side information.
I guess the only thing classically that you need to be careful about are the coins of the malicious verifier, right? If it's randomized.
Sure. Okay. Yeah.
There's also one more question, and that is about composable zero knowledge. So the question is the composable definition of zero knowledge more restrictive than the vanilla zero knowledge? Is there any interesting protocol where the two notions differ?
So it depends what you mean composable. Like sequentially composability, I think, okay, at least if you have side information, I think it composes sequentially without any problem. But we cannot compose zero knowledge, or in general, at least, we cannot compose zero knowledge in parallel. And this because you need to do all these guessings all together, and then the probability that you are correct in all of them is exponentially small. So composability does not hold in general with quantum zero, with even classical zero knowledge. Okay. So yeah, just a side remark is okay. It's a bit funny or interesting that as you saw in the talks by Rotem, like no cloning theorem is helping us by like achieving, let's say, quantum key distribution. And here, like quantum no cloning also harms us, right? So here, our problem here is that also no cloning theorem is preventing us to do stuff as well. So just a side remark that nothing is all good and all bad in life. Okay, so let's move on. So let's try to solve these problems all together. Okay, so yeah, I guess is there any other question before moving on?
That was it. Okay.
So in order to enable this simulator or enable a simulator to have quantum side information, we will have a technical detour and talk about Watrous' rewinding lemma. And the statement that Watrous approved is the following. So suppose that you have a quantum circuit C that, let's say, run in polynomial time, but it does not really matter. And there exists some value P such that for all possible input state psi, Q running on psi and zeros, it has some output that is square root of 2p, 0, and some arbitrary state phi 0 that depends on psi, and square root of 1 minus p, 1, and some arbitrary state phi 1 that also depends on phi. Okay? So P is just a probability distribution, so it's just something in between 0 and 1. So yeah, let's suppose that you have some Q such that such that we have this property, and here 0 is just to denote any possibly number of 0 auxiliary bits that might have, and the size of psi is fixed. Let's say you have n qubits here. So what Watrous' rewind lemma says that then for every possible epsilon that might choose, you can construct some circuit R and some quantum circuit R, And the size of R is a polynomial in the size of the circuit Q and log 1 over epsilon and 1 over P, such that on input side, the same input that we would like to give to Q, you can output phi 0 with probability 1 minus epsilon. So notice, okay, let's consider the naive algorithm that would output phi 0 is just run Q once, measure the first bit, and if it's 0, output the second register. Okay, this procedure, this naive procedure, would succeed with probability 1 over m. Sorry, 1 over, sorry. How can I go back here? Okay, let me clear. So the naive procedure succeeds with probability p, right? This is the probability that you measure 0. And what this statement says is that you can pick, let's say, epsilon very small, and you can think about it being negligible small on some parameter lambda. And then you can come up with a circuit R where you just have a polylambda blowup, right? Because you have log of this negligible lambda will be a polylambda. So you have not so much bigger circuit R that allows us to extract or retrieve these desired state phi 0 psi. Okay, so this is the statement that Watrous proposed. I'll give some intuition why it works. And but before that, I just like to notice that something similar also works in the non-exact case, meaning that the output here is not exactly p, is some, let's say, some q, square root of q 0 phi 0 plus q plus square root of 1 minus q 1 and phi 1. Of course, phi 0 and phi 1 still depend on psi, and q is, let's say, p more like it's almost p, so it's p plus or minus negligible on lambda, let's say. Okay, so what Watrous proves in general is that this rewinding, some sort of rewinding like this, will work even in this more general case, which is important for when you're talking about computational zero knowledge. But for this lecture, I'll forget about these subtleties, and I'll just consider this this exact case where you have the probability, the amplitude here being exactly square root of p. And so, as I said, we had this naive procedure that just measures this quantum state. That we call this, I don't know, phi. No, not phi. Sigma. So the naive operation just measures the first qubit of sigma, and if 0, we're okay. We have phi 0. But if you the problem is if you have 1, then you're phi 0, and if you have phi 1, you're stuck with phi 1. Okay, so in principle, it's not so like yeah, without being smart. You can think, okay, if you measure these and have 1, then you're lost. Like then you have you don't have the state that you want anymore, and then you cannot retrieve phi 0 anymore. But Watrous came to solve us, to save us, and intuitively, what Watrous rewinding theorem says is that if you're given the state 1 phi 1 psi, you can information theoretically go to 0, phi 0 psi. Okay, so this state contains enough information, or all the information that we need to get the state that you want. And more importantly, we can achieve, like we can extract or can get the state phi 0 psi efficiently. Okay, and this is, I think this is very surprising. That's a very beautiful result. And in order to do this rewinding, what Watrous proposed is this quantum rewinding operation. So we had this unitary Q that we defined before in our lemma. And this rewinding operation is just apply the inverse of Q in this in some state. Then apply this operation on the state after applying Q, and applying Q dagger, and then apply Q again. And let's now focus and understand what this operation is. But in order to do that, let's define this operator delta. And delta is as I defined, is the projection onto the valid initial states of Q. So if you remember what I said, you have this unitary Q that receives two inputs. It receives this input psi, but it also has this auxiliary bit 0. So let's say A, and it outputs something that we like. It outputs something. We don't care what it outputs. Let's consider just the input. So this operator delta is just a projection onto the valid initial states of Q. So what are the valid initial states of Q? So the first register don't care because psi is an arbitrary state, but the second one is just zeros. So what I'm saying by that is that delta is just identity on the first register, tensor projection on zeros on the all ancilla qubits. So in some sense, delta is checking if some state is a valid initial state of Q. And then what 2 delta minus identity is doing? So it maps some state psi and 0 to minus the state psi and 0. And everything that's non-zero, so let every psi and some r, where r is different of 0, it will do nothing. Like, oh no, sorry, it's the other way around. So here it remains the same, and it applies a negative phase on everything else. Okay, to be very honest, this is not very important. What this is doing is just for completeness that I'm telling you. Okay, but this is easy to implement, and this is what this operation is doing. Just applying the inverse of Q, putting this minus phase when you don't have zeros in the supposed register with the auxiliary qubits, and then apply Q again on after you put this negative sign.
There's one question.
Yeah.
And the question is whether there's a difference between this procedure and amplitude amplification.
This operator is the same operator as amplitude amplification, but how we compose them is a bit different. Okay, so how, like the rewinding, okay, they're very similar. So yeah, thanks for pointing it out that I should say it out loud. This appears already in Grover's algorithm, if you remember it from Henry's crash course. But the point is how we use it is a bit different. Okay, but in order to see that this is almost amplitude amplification, let's analyze how it works. So let's suppose that you run the Q. So you have the state of your algorithm after applying Q. So it's just square root of P and the desired state plus 1 minus P, the unwanted state. And as we said, we want just to retrieve phi 0. So let's do the naive thing. Let's measure this quantum state. And if we are in the if we're in the 0 case, great. So this happens with probability P. So we're in the good case with probability P. But with probability 1 minus P, we have the unwanted case, right? So with probability 1 minus P, we are in the unwanted case. But what Watrous showed with this quantum rewinding operator is that if you, what Watrous showed is that if you apply this quantum rewinding operator, on the state 151, then actually you're moving your state, you're staying in this plane spanned by 151 and 050. So that's a good thing. Like you're not going to a very arbitrary and far state. But on top of that, you're going closer to the state 050. So if you assume that your angle that you had before between the original state and 151 was theta, so, and this is the probability of, so this is the cosine of this is the probability that you get in this unwanted state, like the thing that you don't want. After applying this quantum rewinding operation, you're moving further from it. And once you're here, you can repeat it. You can repeat the naive procedure again, right? And measure in the first qubit and check if you have 0. And this now will happen with probability greater than P. In which case, again, you're happy. But if you're not, since you're in this plane, the only thing else that you don't get if you don't have 0 here is that you have 151 again. But again, we know how to move further in the direction of 050, so you can just keep doing this. You measure if you're in the not in the state that you don't want, apply this quantum rewinding operator, measure it again, and repeat this until you decide to stop or until you have the state that you want, until you have measured and you have 0 here. Okay, and this is exactly what this operation R that Watrous defined before is doing. So it's just keep measuring and until you don't have the outcome that you want. Otherwise, just you have then if you don't have the outcome, you have this other state, and but using the quantum rewinding operation, you can recover from it and move closer to the things that you want.
That's one question, and that basically asking you to confirm that this basically only requires black box access to Q.
Yes, yes.
Not a circuit representation.
Yes, yes, yes. And okay, yeah, Q and its inverse.
That's right.
So from these, I think it should not be very hard to see that if you repeat enough times, so if you repeat something that is polynomial in inverse P and some inverse the logarithm of the inverse error that you want, you should output the right state. Okay, there's some negligible with probability 1 minus epsilon minus some negligible that don't care too much. Okay, so is there any question about the final statement that you have from Watrous rewinding and how? And yeah, we are still explaining how you use it, but at least how to gather intuitively.
There isn't for now. So
okay, thanks. So let's go back to so after this parenthesis, this technical parenthesis, let's go back to this simulator for this quantum simulator for this classical protocol. And instead of having the previous simulator, let's define some simulator that I call sim1. Then you should think that you have sim2 later. And now this simulator, it expects some side information psi, and this can be arbitrary. It can be a quantum state or whatever. We don't really care. And this simulator just picks some uniform, picks some uniform edge, commit to a coloring that is consistent with that edge, so where the nodes of the colors of the nodes of E they are different. Give it to V tilde, receive the challenge, and then when you receive the challenge back, you check if E is different of E prime. In each case, oh no, okay, this is equal. So sorry, this should be equal. If E is equal to E prime, you just move on, like open the commitment and forward the output. Otherwise, you decide to abort. And as we had discussed before, if E is equal to E prime, then the output of the simulator is good. So if you're lucky and you got the right E prime, then you're good. And this happens with probability roughly 1/n. So you have these negligible things that I won't worry about it now. Like let's say the probability is exactly 1/n. So you can think that, okay, before measuring, so instead of running this simulator like and doing measurements, you could just think that you're doing this superposition, and you could have a superposition of let's say the 0 if this simulator succeeds, and the corresponding state phi 0, meaning that this is the state when you have the after you like when you succeed the guessing, and this happens with some probability p, let's say. No, sorry, it happens with probability 1/m. We have it already. So this is 1/m. Sorry. I don't know how to erase it. Yeah, anyway. And you could consider the remaining state, the one where you fail. So let's say like this is a flag saying that if you failed, and this happens with probability 1 minus 1/m, and then you have some state phi arbitrary state phi 1 when you don't succeed. Well, I chose carefully the letters that I used here, so it is clear that what you want to do. Our final simulator is just to Watrous grinding on simulator 1. And when you're talking about Watrous simulator, you just have to choose the error that you want at the end. So what's the probability that you don't retrieve the right value? And here you pick, let's say, some epsilon that's negligible. And using Watrous rewinding lemma, we have that this output of the simulator is negligible close to the output when we had E equals E prime. And this is good. So we already saw that this, okay, even in the simulation I had before, when you do the correct guessing, then all you did in the simulation is good. And moreover, since we pick epsilon to be negligible in n, we have the runtime of the simulator is just has a polynomial overhead over the runtime of this black box verification. Oh, sorry, this malicious verification. Is there any question on this?
Yeah, there was a question about the meaning of m and n. So m is number of edges, but what is n?
N is the number of vertices, yeah.
I see.
Yeah. Yeah, okay, they're all related, so it does not really care. So just to wrap up, what I showed is that, okay, this shows that this GMW protocol is also secure against quantum adversaries, and this was the result by Watrous. And we can also, like, if you look carefully, one interesting thing is that, okay, first, this protocol assumes post-quantum commitment schemes. And we can implement them from post-quantum 1A functions if you use, for example, an Watrous commitment scheme. You have more rounds of communication, but we don't really care. I don't really care it for now. I don't really care about it now. So one interesting thing is that, okay, what I try to show now is that, so we have zero knowledge is what we call mini Q-crypt. So this is the world where we have quantum plus 1A functions. So we have that this protocol that is in mini Q-crypt belongs to mini Q-crypt because the adversaries could be quantum and the protocol is not broken. And my goal now is to so this statement, this curler that I just mentioned, it is just saying that this completely classical protocol is secure against quantum adversaries. And we can go one step further and talk about having quantum protocols. And on top of having quantum protocols, you could think more, can you have a quantum functionality? So, and my goal, like in this, for the remaining of this talk, is talking about having zero knowledge protocols, when not for NP, where we have classical proofs, but for the notion, for the complexity class that we call QMA, where we try to define what are when we have quantum proofs to prove mathematical statements. So, is there any question, or if not, I'll just move on to the case where we have quantum proofs.
Yeah, I think we have a question concerning Watrous or rewinding lemma. So in the classical crypto, we usually consider tightness, but in the quantum algorithm, even a quadratic increase of the number of qubits can render an algorithm infeasible. So should we also consider in the quantum setting, like, for example, the number of qubits after the reduction, something like that?
No, I think it's not the number of qubits. I think it's just the runtime. I think Watrous rewinding, it's using the same number of qubits as the adversary. Right? Okay. To be more precise, it's using possibly one extra qubit, but not more than that.
Okay. Thanks.
But okay, and all I'm talking about here is theoretical. So yeah, the question is, can you do tight things? Like, this is a question, like this question I don't touch at all. Like I'm just considering feasibility in the quantum setting.
Okay.
So let me move on. And as I said, NP has a central role in complexity theory, and it has been extended in very different ways in the classical setting. But with the development of quantum computing, we can start thinking about what happens if you have quantum proofs. So in particular, we have defined the complexity class that's called QMA for quantum Merlin-Arthur, where both the prover and the verifier are quantum parties. And now the prover is able to send a quantum state psi as a proof to this verification algorithm. And the acceptance and rejection probability, they look like the NP ones. So we want that for true statements or for instances in the language, there exists some quantum message from the prover that makes this verifier accept with high probability. And for no instances, no matter which quantum state this prover sends to this polynomial time verification algorithm, it rejects with high probability. And here also, okay, here again, we don't know if you can make this perfect or not. So we'll just stick with high probability.
Let me ask one question here that already came up in the context of NP, but I kind of missed the right moment to ask it, I think. So we don't assume anything about the efficiency of the prover, right? But we do assume the verifier is efficient.
Yeah. For now, we don't think about the efficiency of the prover.
Okay, thanks.
Like, of course, when you're devising cryptographic protocols, then they start appearing, as Thomas was describing yesterday for delegation. Even for zero knowledge, this is important sometimes, but for these lectures, the prover could run in exponential time. And OK, once you have defined a non-interactive, like one message quantum proof verification, OK, you can say, well, OK, let's be crazy and do multiple rounds of interaction between this quantum verifier and quantum prover. Again, we want that the true statements, they should be like there exists a prover that convinces the verifier of true statements with high probability. And here we can even say that with probability 1. And for false statements, no matter what this quantum unbounded prover does, the verifier should reject with high probability. And it turns out that this ladder, like when you have quantum interactive proof systems, it is actually equal to p-space and therefore equal to the classical setting. So in general, like when you don't talk about number of rounds, you have that quantum interactive proof systems are equal to classical interactive proof systems. Qualitatively, we have a bit better round complexity, much better round complexity when you have quantum. So for example, we know that a QIP with 3 messages is sufficient to have p-space. So in some sense, QIP protocols, they have some nice properties, but the computational power of these two models are the same. And in particular, we expect that QMA to be strictly stronger than NP, so quantum proofs to be a very powerful resource, and that the interaction in the quantum setting to be different of interaction, sorry, non-interactive version, which all equal to p-space. And just as a side remark, okay, why should we study quantum proof verification? And actually, this goes more in fundamental and more physical questions, but it turns out that QMA is a very natural, QMA have very natural complete problems. And I'll talk about one of them later. So it's not that we're just extending NP to put in the quantum setting, is that there is a meaning and there are important questions that are related to QMA. And let's now talk about quantum zero knowledge. But for that, let's just recap what we had before. We had this classical protocols that are classical zero knowledge protocols that are secure against quantum adversaries. And when we're talking about quantum zero knowledge, it's just that we allow this prover to be quantum as well, but nothing else changes. Like the security definition, like the zero knowledge property is the same as we had before for classical protocols. So this does not change at all. It's just that the protocols in the honest run, they should use quantum resources as well. And with that, okay, our goal is to have quantum zero knowledge for QMA. Okay. And the first thing that we could think, okay, can you have a zero knowledge from this generic problem in QMA? But when you think about the classical setting, we don't do a zero knowledge protocol for an arbitrary NP problem. Like you need a lot of structure. We're doing it for a complete problem, for like a specific NP complete problem. So we can think, okay, so you have this local Hamiltonian problem that is that's a very important problem in condensed matter physics, and it is QMA complete. So let's do a zero knowledge from this complete problem. And here, the issue is that we need much more structure than local Hamiltonian problem. So again, going back to the classical case, we don't do zero knowledge protocols for SAT, because SAT does not have nice properties or not nice structure that allow us to do zero knowledge. We do it for a specific NP complete problem, that's 3 coloring. So let's fix what these local Hamiltonians are. I didn't explain what they are, but it's not important. So let's fix some subfamily of local Hamiltonian problems. And then we have enough structure. Then we have zero knowledge protocols for this specific family of local Hamiltonian problems that turns out to be a QMA complete. But this is not a very, I don't know, clean zero-knowledge protocol as we had before for three colors. So that's not the, at least for introductory lecture, this is not the right protocol to explain. And finally, we got to the one that I want to talk about is zero knowledge from this problem that's called consistency of local density matrices. And let me first explain what this problem is. And the question that we want to study in this problem is, if you're given pieces of a quantum state, is there a global state that is consistent with all of them? So let me just give a step back and talk about the classical version of this problem. Imagine that you're given a description of marginals of classical distributions on, let's say, k bits, or k is a constant, and you want to know if there exists a global distribution on n bits that's consistent with all of these marginals. This problem turns out, like the classical problem turns out to be NP complete. But now here we're trying to have the quantum version of this problem. So we want to like, the idea here is that you have this description of the density matrices. So you have this 2 to the k by 2 to the k matrix. And these are density matrices, as Henry described in the crash course. And the question is do they all come from the same quantum state? So let me be a bit more formal. So if you're given as input this k by 2 to the k by 2 to the k matrices on each one of k qubits for a constant k, is there some state psi, like on n qubits? So is there some psi such that when you look locally to these parts of psi, so that's what tracing out means. So when you look to these parts of psi, then they look like all these density matrices that were given rho I. So you want some psi such that all of these local reduced matrices of psi are very close to rho I. So let's say that's negligible in n. Or if not, like we have a problem here, or if no matter which quantum state psi you have, there exists one rho I that is far from the reduced state psi on the corresponding qubits. Okay, so we have a promise problem, so we don't care about things that don't fall in the yes case and the no case. Is there any question about the definition of this problem?
For now, it doesn't seem so.
Okay. So Yikai Liu showed in 2006 that this problem is in QMA. And he also showed that this problem is QMA hard under Turing reduction. But unfortunately, Turing reductions are not good in order to do zero knowledge protocols. So like if you had a zero knowledge protocol for this problem and it's only QMA hard under Turing reductions, it does not mean in general that you have a zero knowledge protocol for QMA. But then last year with Annie Broadbent, we finally showed that this problem is indeed QMA hard under CARP reductions. And this is a standard type of reductions that maps yes instances to yes instances and no instances to no instances. And with this new type of reductions, it allows us to propose zero knowledge protocols for this problem. And these will directly imply zero knowledge protocols for QMA.
Just one clarification question about this slide. So what is SI bar?
Oh, okay, sorry. So let's say that rho I, so it sits in some, like it should be described on some set S1 of qubits. So this is the set of SI is the set of qubits where rho I is supposed to sit. So the point is, okay, you need to give the description as well. So you have SI. So it's just saying that, okay, I give you this 2 to the k matrix, and it should sit on a specific position of this global n qubit state.
And SI bar is the complement of it.
Oh, sorry, yeah, SI bar is the complement. So okay, this is just saying that if I remove everything that's not an SI, do I have rho I?
Thanks.
So our goal now, okay, given this technical result that this problem is coming hard, our goal now is just to prove zero knowledge protocol for this problem. And for that, I need to quickly say some properties of how to put this problem in QMA. And I don't want to get into details, but the idea of this inclusion is that the prover is supposed to send L copies of this state that is supposed to be consistent with all of these reduced density matrices. The verifier will pick one of these density matrices uniformly at random. And there is some checks that the verifier can do only by verifying that the qubits that correspond to this density matrix rho I. Okay, so this is the important property that I want to highlight here, is that after you pick some I uniformly at random, you discard all the qubits but the ones that correspond to this qubit rho I. And what Ikai showed is that, okay, there is this test that you can do, such that for the yes case, if there exists some state psi that is consistent with all of these density matrices, then the verifier should accept with probability negligibly close to 1. On the other hand, for soundness, what he shows is that if the prover sends an arbitrary quantum state sigma, so it should not be in a tensor product, so it can be an arbitrary state, we still have the same verification, so the verifier picks this uniform, so the verification should be the same, so the verifier picks this I, looks to the specific regions that should correspond to rho I, perform the verification, the checks, but then what you can show is that doing this, like if you do these checks, the verifier accepts with probability smaller than 1 minus 1 over m. So you have an inverse poly gap between yes instances and no instances. Again, I don't want to get into details which checks you do, yeah, I think these are the only bits of information from this proof that I think are relevant for the zero knowledge protocol. Is there any question about this QMA verification? So let me move on. So let's go to the zero knowledge protocol. So, so the idea is that the verifier has this input to this CLDM problem. So it has m density matrices on k qubits. So it has m pieces of a quantum state. And the prover, since we're considering yes instance for zero knowledge, we assume that prover has L copies of the state psi that's consistent with all of these rows. And we don't know how to do, we don't know how to put qubits on a safe, but we can do something that's almost as good as that, is that first we apply this one-time pad on this state psi. So you pick random x operators and random z operators and apply on each one of these qubits of psi tensor L. And we keep, of course, all of these one-time pad keys aside, such that we can undo the one-time pad on this quantum state. But you can notice that if you pick them at random, these are classical objects, and these one-time pad keys, these are information that you can put in a box. And this one-time pad of this quantum state, together with this commitment of these one-time pad keys, is the information that the quantum and classical information that the prover sends to the verifier, of course, by picking, or sorry, by keeping the the keys that open these safes. I'd like just to point out that Henry, I think, mentioned that. Okay, we have that if you have the hiding property of the commitment schemes, if you know that the verifier does not know anything about what's inside it, these safes, we have that this quantum state that the verifier holds should be uniform, like totally mixed, meaning that the verifier has zero information about it. It's fully one-time padded, and the verifier has zero information about it. The protocol then follows by the verifier just picking I in format random and sending to the prover. And the prover now sends the one-time pad keys that, sends the opening of the commitments of the one-time pad keys of the qubits of row I. So the idea is that here, this verifier is supposed to hold many copies of qubits. Many copies of the state, but all of them are one-time padded. And the prover will send the keys that will allow the verifier to open the commitments and undo the one-time pad of specific regions of this quantum state. So these are the only regions that the verifier will be allowed to read from this quantum state. And moreover, we know that this state psi, we're in IIS instance, so we know that the state psi, when you look to these regions, they should indeed contain the density matrix rho I. See, these are the only things that should appear here. So this is the intuition why this protocol is zero knowledge. But and again, we have this protocol is complete and sound, and the idea here is that given assuming that the binding property of these one-time pad keys work well, then the verification that the verifier is doing this zero knowledge protocol is the same one as she was doing in the QMA verification. So she's just looking to specific positions of this quantum state. So the QMA verification can be reproduced in the zero knowledge protocol. I already gave an intuition why this protocol should be zero knowledge. So intuitively, you have this part that will be unveiled to this verifier are exactly this a quantum copy of this density matrix rho I. But again, the verifier has a classical description for Y, so intuitively, this verifier is not learning anything. But again, in order to prove zero knowledge, we have to come up with a simulator. So is there any question about this protocol?
Yes, there's one question, and that is whether the prover has to send all the copies of the state in advance, or whether he can send them on the fly.
No, he has to send it in advance. And the point is, imagine that he does not. So imagine that, imagine that he does not. So, imagine that you don't have this here. And the verifier sends some I. Then the prover can, once this prover has I, he can come up with some state, let's say psi I, that passes the check for psi I, for I, and send XAZB psi I tensor L together with the openings. And this completely passes the check, no matter if you have a yes instance or no instance. So it's crucial that the verifier receives the state along with the commitments.
Thanks.
So let me go through the zero knowledge. property. So we again have this simulator 1, but now it proceeds as follows. So it gives all bad naming. So psi here is the side information. Okay, so the simulator gives the side information to v tilde. It picks some I uniformly at random. And this is a guess. And then the verifier can commit to that state, let's say phi I, that passes the check for the specific I, and send all the commitments to the verification, or to v tilde. V tilde then answers with a challenge I prime. And if I is equal to I prime, the simulator just behaves as normal. So just open the commitments of the one-tapped key of the corresponding qubits that we know that are equal to rho I because you constructed the state phi I to be consistent with rho I. So the verification algorithm won't see the difference. So it turns out that the same properties that you had before with the classical protocol remain here. So if I is equal to I prime, then the simulator works. And the simulator succeeds probability 1/m up to negligible, like that I've ignored for now. So you shouldn't be surprised that, OK, the full simulator is just applying Watrous rewinding, and the same, exactly same argument that you had in the classical setting works here. So you just, like the output of the simulator is negligible close to this output of the simulator 1 in the good case. And the run time of the simulator just has a polynomial blow up on the runtime of the malicious verifier. Okay, so this analysis is just a straightforward generalization of the classical one against quantum adversaries. So yeah, I don't know if it was too fast or if people have other questions.
Let me ask one question that has not been asked by other participants. How do we get the guarantee that that the simulator can prepare such a state phi I that's consistent on subset I?
Okay, so rho I, we have rho I is a quantum state, like K is a reduces matrix on K qubits, where K is a constant. So rho I is it's just a density matrix on 2 to the k by 2 to the k, right? And given a description, you can efficiently compute like constant an arbitrary quantum state that matches this density matrix up to exponentially small precision.
Okay, thanks.
Like it's just, yeah, the key point is that this has constant size.
Right. And then there's also one more question about the last slide, and that's apparently kind of a clarification of the previous question. So the question was whether so there's many copies of the state psi on the last slide, right?
Mm-hmm.
The question is whether you can process the copies one by one, like sending one-time pad encrypted state, then getting the challenge and sending the response. But it seems like the challenge is the same for all of the copies.
No, we don't, because for the QMA verification, we need to check all of them in parallel. So I can talk about this offline, but I don't get into details. But the point is, this QMA verification, it assumes that you need to process all of them, like L copies in parallel.
I see. Thanks.
So yeah, I'd like just to finish the zero knowledge part. Okay, then what you have is that you also have quantum zero knowledge proofs for QMA in mini-QCrypt. So that's the overall statement. And I'd like just to finish that. Okay, in the past few years, there has been a huge development of quantum zero knowledge, and I just want to highlight a few of them. So for example, in this work with Slofton and Yuan, we we quantize the BJW, saying that it shows that multi-prover entangled proof systems, they're also closed under zero knowledge. So, and this is very like, you should have seen this recent result by awesome, like, yeah, I don't want to cite any co-authors because I'll forget someone, that shows that MIP star is equal RE. So this, this shows that even the halting problem can be proved in zero knowledge when you have multiple quantum provers. And very nice recent result also showing that you can have post-quantum zero knowledge protocols for NP or QMA in constant round, even in the plain model. So you need some strongish assumptions like LWE, but still we can do like constant round zero knowledge for these classes against quantum adversaries. There is a notion of proof of knowledge where usual soundness says that you don't have a good strategy for like the prover. If it's a no instance, the prover cannot convince the verifier. And proof of knowledge go one step further. So that when, for instance, you're talking about proof of knowledge for NP, the prover can make this the verifier accept if he knows a quantum. If he knows NP witness. Finally, we can start thinking about classical protocols for QMA, and there has been some results in this direction. And even if you have non-interactive zero knowledge. And okay, this I just want to quickly go through them. I think these references could be digested later by you, and but I'd like just to point all of them out. And if there's any other question, I'll switch gears and start talking about multi-party computation. Okay, so let's move on. And in a protocol for multi-party computation, we have k parties. Let's say these 8 parties. Each one of them has an input. Let's say x1 up to x8, and they want to jointly compute this function f on their inputs, but without revealing the input to each other. Let's say that you have some sensitive data. I don't want it to be spread among all of their people. So if we have an ideal world where we have this trusted party that everyone can trust and send information and know that that the information will be kept private, we can think that all the parties send their input to this trusted party. This trusted party just computes the function and send it back to all of the parties. And in this ideal world, we can be sure that each party only learns the output of this function and nothing else, right? By definition, the only information that I got from the trusted party is the output of this function f on the chosen inputs. But of course, we don't live in an ideal world. So, and our goal is to implement protocols that implement this ideal functionality. So in particular, we want to devise protocols where all parties can talk to each other, they should talk to each other. But still, the only thing that they should learn from this protocol is the output f, like the output f. Oops. And this should be true even if all but one party behaves dishonestly, for example. So we want that this single party here that is honest, she should be able to have her input private, even all of the others collude and try to learn her input. And multi-party computation is a very hot topic in cryptography. And there are plenty of protocols, implementation, yeah, it's a very beautiful line of works. And here, what studying these protocols, like a multi-party computation in the quantum setting, we have three types of questions that you can ask. So for example, we can ask, are classical protocols secure against quantum adversaries? So if now that you have this classical protocol, if all of these malicious parties, they do have quantum computer, can you still enable privacy for the honest party? The second type of question is, imagine that these parties, they want to have to compute this class of functionality, but now we can assume that they all have quantum resources. So can you have, with these quantum resources, better quantum protocols for this classical functionality? And finally, the question is, can you have protocols when these parties, they want to compute a quantum function? So they don't share, like, they imagine that they share quantum states and they want to compute a quantum operation on this quantum inputs. So can you have protocols that enable them to do that? Okay, and this is something that I'll discuss for the rest of these lectures. But in order to start, I'd like just to recall what is the secure definition when you're talking about multi-party computation. But for simplicity and for my drawing skills, I'll just talk about two-party computation. And here, okay, when you're talking about dishonest majority, we assume that there is one party that is honest and all the other parties are, sorry, one party is honest and all the other parties might be dishonest. And in the real world, we just have the assumptions that each party receive their supposed input, and they have their, and after running the protocol, they should output something, right? This is the only thing that we can assume from these protocols. And our goal is to show that whatever this malicious party can do in this protocol, we can translate their actions to this ideal world, where the honest party is somehow secure given this idea functionality. So you have this idea functionality that computes the function f that you want, and this honest party only interacts with this idea functionality. So as we saw in the trusted case that I just mentioned, we are sure that when you're talking about trusted parties, these inputs, for example, xb that B receives, will never be leaked to other parties. So as I said, our goal is to show that no matter what this malicious adversary does in this real world, we can come up with a simulator in this ideal world that might interact or will interact with a black box or white box, I don't care, with this malicious party and with this idea functionality. And the simulator, after interacting with these two parties, should output something. And our goal is that no matter what distinguisher, or at least or polynomial time distinguisher that covers these two cases, so no matter which distinguisher that gives inputs and read the outputs of these two protocols, should be able to distinguish them. So more precisely, so for every D that interacts with these parties according to these arrows, the behavior of this distinguisher in the real world and in the ideal world should be equal up to some negligible factors.